In this video, we'll talk about solving systems of equations using substitution. In particular, here we'll be looking at linear equations. So the concept of systems of linear equations, and we've talked about how to do them with graphing, and we've talked about numbers of solutions. So say we have two lines, and let's say for the sake that they do intersect. At this point of intersection here, this is technically a coordinate. And both of these equations can be written as linear equations, which would be y equals mx plus b. They may not necessarily be in that format, but we can write them as such. So what that would mean is that for both of these equations, when I plug in the x value of that green point in for one equation, and the y coordinate in for the same equation, I should get the same thing as if I plug it into the second equation as well. So say I have, I don't know, for example, a different y equals mx plus b. Well, then I should get the same thing if I, plug the x in for the x and the y in for the y. I should get the same values. They should both work, is the concept we're playing with here. So when we're looking at these two equations, we know that if we're looking for that point of intersection, these x's and these y's are all equal. And that's not the case if I look at, two different points, not the case. But for this one green point where they meet, it is true. They are equal. So that's kind of the driving concept here, and we'll kind of talk about some examples of how that works. So if we look at an example here, and let's say for the sake of ease of this first example that both of these are in slope-intercept form. So they're of that format, y equals mx plus b, and we know that the y's have to equal the y's and the x's all have to be equal, right? So this x is equal to this x, this y equal to this y. Well, if both of these expressions are equal to y, which we know to be the same thing, well then can I deduce that 2x plus 1 is equal to 5x plus 2? I think that we can, because at that point of intersection, and only at that point of intersection, the x coordinates are equal and the y coordinates are equal. So I can use this to determine at least what the x coordinate is, and then I can plug it back into either equation to solve for y. So if we were to solve this equation, we could subtract 2x from both sides. So we'll have 3x plus 2 is equal to 1. Subtract 2 from both sides, so negative 1 equals 3x. And then I can divide by 3, so x equals negative 1/3. And then once I have an x coordinate, I can plug it back in to either one of these equations. It should work out the same. I'll do both for the sake of the example here, but in reality, when you're doing this in practice, you only have to plug it into one. So all things being equal, pick the one that'll be easier. So I'll plug it into this top one first, just to kind of show that it works. So y is then going to equal 2 times negative 1/3 plus 1, which will mean that y is going to equal, looks like negative 2/3 plus 1, which will mean that y has to be 1/3. Now, normally in practice when we're doing this, that'd be good enough. I'd stop there. But to show you that it does work if I plug it into this equation as well, we'll just demonstrate that it does work. So I'll take 5 times negative 1/3 plus 2, which then we can say, this will be negative 5/3 plus, and I'll go ahead and convert 2 into thirds, which would be 6/3. Y is going to equal 1/3. It is the same. It does work out. Like I said, in practice, you wouldn't bother doing this second one, but it does work. It doesn't matter which one you plug it into. All things being equal, plug it into one that's easier. In this case, it was kind of the same either way you go, but sometimes there is one equation that's definitely easier than the other. So that's the kind of idea behind substitution. I'm going to try and pick one of my variables that I can isolate early on, and then I can substitute that value in for the other variable. So let's look at another example here. And on this one, we have a couple of options. So one equation is in slope-intercept form. That makes it pretty easy to work with. The other one is not. So we have two options. We could either convert this bottom equation into slope-intercept form, or we can kind of do an altered version of substitution. If we look at this, y is equal to 2x minus 4. Well, there's y right there in the second equation, so why can't I just substitute, instead of using y, 2x minus 4? So then ultimately it would look like, if I run this down one more step, 3x plus 2 times 2x minus 4, because this is y. It's just a funny way of writing it. And we're going to say that equals 12. So this is just an alternate version. We can use it if we want. And we can kind of just do a portion of substitution here. It can sometimes save you some work algebraically. It all depends on what you're comfortable with. Now, you got to be very careful with your parentheses here. Like in this case in particular, we're multiplying y by 2, and if y is an expression of more than one term, we have to make sure we double all of it. So I'm going to go ahead, simplify my left side of the equation a little bit. So this will be 3x plus 4x minus 8, and that's going to equal 12. Let's go ahead and add 8 to both sides, so we'll have 20, and then I'm going to combine the 3x and the 4x to make 7x. And then in this case, x is going to equal 20 over 7. Now, me personally, I like fractions. I'm going to leave it that way instead of reaching for a calculator and trying to get some sort of decimal equivalent, because sevenths are not nice. So that's a perfectly adequate coordinate there. So now we're going to take this x value and we're going to plug it back in. And all things considered, I think plugging into the top one is going to be easier than trying to plug it into the bottom and solving for y. So let's plug it in. Y is then going to equal 2 times 20 over 7 minus 4. So let's go ahead and simplify a little bit. So we'll take the 2 times the 27ths, which would be 47ths. And then I'm going to go ahead and I'm going to convert this 4 into sevenths. So that would be, minus there. Oops. Let's fix that. Okay, I'll make it a big negative sign. And this will be 28 sevenths. So if we take 40 minus 28, that would leave us with 12 sevenths. And again, fractions are just fine. They're exact. They will work every time. Now, another way you can write these solutions, because it's generally understood it's a coordinate, you can write it as an ordered pair. So you can write it as x is 20 over 7 and y is 12 over 7. That would work too. Both of those are totally adequate ways of doing or writing the solution. Now, sometimes when you're not talking about x's and y's, that's where it's a little bit weird. If your variables are s and t or r and q, then you want to give more of the equation style, where x is this, y is this, or in the case of like r and q, say r equals this, q equals this. So one last example here. This one, I have both of my equations not very nice to work with. I'm going to have to do some algebraic manipulation here. I got to isolate at least one variable. So here's what I'm thinking. Let's rewrite this top equation. I'm just going to go ahead and subtract 2y from both sides. So then x is going to equal 3 minus 2y. And I could try and manipulate this equation down here, but that's going to be kind of not fun. I'm going to have some kind of ugly fraction in there. So the thing that people, or I have seen in the past, is that there's this obsession to get y by itself. You can do substitution with an x value. You can treat it just like you would a y value. So in this case, I think I'm going to plug my expression in here for x and solve for y first. So the order doesn't so much matter. Go with the path of least resistance. Don't work any harder than you have to. So I'm going to rewrite this second equation, but instead of x, I'm going to use this expression 3 minus 2y. So 4 times x, which is 3 minus 2y, minus 3 more y is going to equal negative 20. And now I'm going to solve this equation for y. So we'll distribute in the 4. So we'll have 12 minus 8y minus 3y is going to equal negative 20. And then we can combine some like terms. So 12 minus looks to be 11y is going to equal negative 20. And then we can subtract 12 from both sides. We'll have negative 11y equals, looks to be negative 32. And then we'll divide by negative 11. So y is going to equal positive 32 over 11 because they're both negative. And again, it's a fraction. It's not nice. This is an exact solution. Let's just leave it as such. Now we've got an option here. We have y value, so we could plug it into either equation. All things being equal, I say let's plug it into this one right here. And then we can get x by itself and we can solve. So let's plug it in. That means x is going to equal 3 minus 2 times 32 over 11. Okay, let's simplify a little bit. I'm going to go ahead and write the 3 in terms of 11, or 11ths, I guess, just because I know that's coming. So let's call it 33 out of 11. And then we'll double the 32, which will be 64 elevenths. So I'll take 33 minus 64, which should be, I believe, 31. So x is going to equal negative 31 over 11. And then at that point, we have our solution. We could also write it as an ordered pair, if we so choose. So, or negative 31 over 11, comma 32 over 11. That would also be an acceptable way. We just have to be very careful that the x-coordinate comes first, the y-coordinate comes second. So there's a bunch of different ways we can use substitution. The idea is we are trying to create an equation with only one variable that we can solve. And then once we know what one variable is, we'll plug it into one of the original equations or an altered version of one of those equations to solve for the other variable.